Okay, it's 1 o'clock. Okay, so welcome everybody to the Fields number 30 seminar. I hope you're having a wonderful summer wherever you are and that you're keeping safe and healthy. We're delighted to have as our speaker today Liyang from Caltech, and he'll speak about holomorphy of adjoint L functions for GLN and less than equal to 4. Liyang.
Thank you. Thanks for the invitation and thanks for the watching. I'm glad to be here, and in this lecture, I will talk about holomorphic continuation of adjoint L functions for GL3 and GL4. This is part of my thesis topic suggested by my advisor, Dinakar Ramakrishna. I like it a lot, so hopefully this is interesting to you. And here's the arrangement. Here's the arrangement for this talk. First, I'll introduce you some holomorphic conjectures like Dedekind conjecture, Artin conjecture, Selberg conjecture, and then Langlands philosophy. And then we'll provide our results towards some cases of these holomorphic conjectures. And then we'll introduce the main idea of the proof, at least some ingredients. And our main toolkit is a variant of trace formula, and we will call it Jacquet-Zagier trace formula. Roughly speaking, it's a weighted version of the celebrating also-Selberg trace formula by an Eisenstein series. We'll talk about this later, and then we'll give some application of this holomorphic continuation to the horizontal Sato-Tate problem on GL3, as well as some related discussion on beyond endoscopy. So let's start with a folk conjecture by Selberg. And now you can pick your favorite L function in Selberg class. For example, the Riemann zeta function, Dedekind zeta function, automorphic L function attached to some Caspita representation pi, or the Rankin-Selberg L function, or Artin conjecture, Artin L function, where rho is some Galois representation here. Well, technically speaking, not all these L functions are proven in Selberg class for the moment, but they should be, they're expecting to be. Like if you assume Riemann-Newton conjecture for pi, then these automorphic L functions are in Selberg class. And if you assume analyticity of this Artin L function, then it should be in Selberg class. Anyhow, they should be most fundamental and interesting objects in number theory. And we further assume that this Ls has a pole of order R at S equal to 1. Under this citing, then Selberg conjecture that this Ls should be divided by the R's power of Riemann zeta function, in the sense that the ratio of this Ls and zeta to the R should be entire, and the whole should be entire, or it means a holomorphic continuation to the whole complex plane. And you can see this conjecture is related to many other conjectures like Dedekind conjecture, Selberg, Artin conjecture, Selberg conjecture, and some Langlands conjectures in a few minutes. And in the motivic case, it's actually related to a conjecture of Tate. Anyhow, we are expecting Selberg's principle to play an important role in number theory and should be interesting. However, this full conjecture is wide open, even for the simplest case. But that means just assume this L function has a simple pole at S equal to 1. And we are looking at the following two cases. One is for Dedekind zeta function, and the other is for Rankin-Selberg L function. And according to this principle, these two ratios should be entire. And these two objects are the main thing we will talk about in this lecture. So let's look at the simplest case. When K is a quadratic extension and pi is some modular form. Where in this case, we have the following symbol table. And since the Dedekind zeta function, Riemann zeta function, and the Rankin-Selberg function all have a simple pole at S equal to 1. Therefore, these ratios should be holomorphic at S equal to 1, as they are just meromorphic functions. Where that Selberg's principle actually predicts much more. It predicts that if these ratios are holomorphic at this single point, they should be holomorphic everywhere. That provides a quite rigid holomorphy of these L functions in Selberg class. So where this can be seen easily from the algebraic side, because it's just a quadratic extension. The ratio just becomes a tertiary L function of some quadratic characters. This quadratic character is associated to the field extension, where on the analytic side, things would be much less trivial. It's actually a theorem of Shimura and Zagier that this analytic thing is holomorphic as well. And we will now review some historic motivation for looking at these two ratios. Let's start with algebraic part first. It's initially it should be a problem of Dedekind. Dedekind studied the ratios of Dedekind zeta functions of the field extension, and he conjectured that these ratios should be holomorphic everywhere. And we've already seen this for quadratic fields, right? And Dedekind himself proved this conjecture for cubic field. And nowadays we can look at the complete zeta function version of Dedekind conjecture and still expect it to be true. And nowadays, due to the work of Ramata Brouwer and Uchida van der Waal, we know this conjecture holds for several cases like Galois extensions or solvable extensions. So in particular, if the degree of this extension is less or equal to 4, then the Dedekind conjecture should hold. And Murty proved the twisted case. In this talk, we will use the twisted case as well. So there are many other mathematicians interested in Dedekind's problem. Here, we will introduce Artin's work. Artin looked at this problem in some new perspective. He, together with Takaki, proved the following decomposition. Basically writing the ratio of Dedekind zeta functions into a finite product of Artin L functions. I think we mentioned Artin L function before. It's initially defined by local product of L factors from Galois representations, and the infinite product converges absolutely when the real part of S is large enough, namely on some right half plane. And nowadays we know it admits a meromorphic continuation. Since Dedekind conjecture, the left-hand side should be holomorphic. And according to this decomposition, it's very natural to have the following conjecture, the Artin holomorphic conjecture, which basically says that each factor showing up here should be holomorphic. Therefore, you can see immediately Artin conjecture implies Dedekind's conjecture. Well, unfortunately, we don't know much about Artin conjecture now. Basically, it's known from non-mirror representations or some two-dimensional case, like tetrahedral case or octahedral case. And I think we proved this conjecture over function field, but still wide open for a number field. There might be many strategies to attack Artin conjecture, but here I'll introduce my favorite one, which is Langlands philosophy, because I'm a big fan of Langlands. And roughly speaking, according to Langlands, each Artin L functions should be eventually equal to some automorphic L functions, namely the L function attached to some automorphic representations, like the L function attached to module forms, for example. And typically, these automorphic functions are much easier to be proven analytic. We have plenty of tools, many tools to prove analytic continuation of automorphic functions like integral representation or like Langlands-Shahidi, etc. And also, we will see on the other hand that the Langlands philosophy would directly indicate the entirety of the analytic ratio we mentioned before. So now let's look at Langlands philosophy. We'll start with Langlands Correspondence. Here's a very rough introduction. We'll take G to be a reductive group for example, you can take G to be GL2, and LG will be denoted by the dual group. For GL2 is just GL2 of C, and let A of GP be the set of automorphic representations on G of A, and you can think this guy as just as a subspace of the L2 functions on the automorphic quotient of G, and we'll take pi to be a automorphic isobaric representation, or you can think it's just as a Caspidal representation, and then we can look at the standard L functions of pi, and we'll let WF prime be the Waidling group of a global field F, where technically this is hypothetical, but bear with me, because this is just a very rough introduction. It's maybe a motivation. Then Langlands conjectured a map from the set of automorphic representations to the set of Waidling representations or Galois representations, for simplicity. Technically, we should modulo these inner isomorphisms, but these are just some Galois representations, and we will call them parameters. And this conjecture makes sense locally because we can define Wade group over local fields. And for GON, this map is indeed should be bijection, because the L pact for GON is a singleton. So you have a pi here, you have an automorphic representation pi here. For example, you have a Caspidal representation pi here, and it's mapped to a row here. And for row, you have the Artin L function, Ls row. And for pi, you have the automorphic L function, Ls pi. According to Langlands, these two L functions should be equal. So if you can prove the analytical continuation of the automorphic L function, then you will prove Artin conjecture as a byproduct of Langlands. That's basically how Langlands implies Artin conjecture. And then knowing Langlands correspondence, we can talk further about Langlands functoriality. It's roughly this diagram. So given automorphic representation on G, like a Caspidal representation on GON, and according to Langlands correspondence, there's a parameter Galois representation here. Let's call it little phi. And if furthermore you are given an L homomorphism, or equivalently a finite dimensional representation of the dual group, let's say R, then you can consider the composition of these two homomorphisms and call it a capital phi. And this capital phi will give you a new parameter, Galois representation, m-dimensional Galois representation of the Waidling group. And then you can apply Langlands correspondence once again with respect to this parameter. There's a unique automorphic representation on GLM, because for GLM, the Langlands correspondence is it's a bijection. And we will define the Langlands L function with respect to this representation R to be the Artin L function associated to this parameter. And according to Langlands correspondence, this Langlands L function associated to R is eventually the principal L function of the standard L function of the automorphic representation, capital pi. So in many cases, actually in most of the cases, I think this L function should be entire. That's the rough idea of Langlands philosophy, and here is a very concrete and basic example. Just look at the GON case, and we know that GON acts on the Lie algebra of SRN by conjugation, and this will induce a finite dimensional representation of GON of C, which we will call it adjoint representation. It's of dimension squared -1. And you can view this representation as an L homomorphism between the L groups. So you can look at the Langlands L function attached to this representation. And precisely this L function would become the ratio of this Rankin-Selberg L function and Dedekind zeta function. Here, lambda means the complete Dedekind zeta function. And by Langlands correspondence, it should eventually be equal to some automorphic L function. Therefore, we have the following summary. I will call this Langlands implies everything diagram. Literally, Langlands implies everything we mentioned before. So according to Langlands functionality, we can expect the following conjecture, that the adjoint L function should be holomorphic. And this should be a basic result of Langlands functionality. And if you're a big fan of Langlands as me, it should be, this might be interesting to you. However, this conjecture is not known for Hell rank case. Basically, what we know is just a GL2. And here are some other reasons to look at this conjecture. Recall from Artin-Takaki decomposition, we can write the ratios on the algebraic side to be a finite product of Artin L functions, but we don't know each Artin L function is holomorphic or not. And on the analytic side, according to Langlands, we are expecting a similar decomposition, writing this ratio as a finite product of automorphic function attached to Caspita representations, where this is some multiplicity. And we don't know if such a decomposition exists or not, but we do know each factor here should be a holomorphic. So it's like on the algebraic side, we have this decomposition, but we don't know each factor. On the analytic side, we don't know if we don't know such a decomposition, but we do know each factor. So it's sort of like unbalanced, where sometimes life is difficult, but that also makes number theory so charming. And we will look at, we'll investigate this special case without referring to this hypothetical decomposition. Let's look first at what was known about this ratio. As we mentioned before, it's a theorem of Shimura and Zagier, and that this ratio is holomorphic for GL2. Actually, it's proved this for classical forms. And then Shimura's approach was generalized by Gilbert and Jacquet to number field in terms of automorphic representation and complete L functions. And they can further prove the adjoint lifting called Jacquet-Zagier lifting from GL2 to GL3 by converse theorem. And we'll talk about that later as well. And the Zagier's original proof was generalized by Jacquet-Zagier to number field in the framework of automorphic representation, where Zagier's initial proof was using a variant of trace formula, and we will call it Jacquet-Zagier trace formula, and that will play a role in our proof to Hell-Rank case, and we'll talk about that later. For GL2, you can have a simple proof. By simple, I mean short proof using Langlands-Shahidi method. You can look at this, look at the parabolic subgroup of SP4, whose levy is isomorphic to GL1 cross SL2, I think. Then you will get basically the symmetric square function from Langlands-Shahidi method. And where for GL2, this adjoint L function is roughly equal to the symmetric square function, just up to some central character twist. And the Flicker also obtained some partial results on GL1 by using a simple Jacquet-Zagier trace formula. However, it's not strong enough to get individual information about the individual adjoint L functions. Here are some other approaches to attack this problem. One of them is, I think, one of them is based on integral representation. It was pioneered by Ginsburg and developed further by Ginsburg himself and Baum, D.Y. Jiang, and Handley. They constructed some integral representations for for adjoint L functions on lower rank, like a GL3, GL4, and compute this, actually verify that for unramified places. So it works for partial adjoint L functions. I think they have some work on GL5, but maybe not quite complete. Anyway, using integral representation, one can prove the holomorphic continuation of partial adjoint functions to some right half plane. I think one of the best results was due to Handley and Zhang, maybe last year, for Caspidal representations on GL3. They can prove the finite adjoint L function is holomorphic in this right half plane. And at the first glance, you may think it's okay because we can use functional equation to get it continue to the whole complex plane. But this would be a little bit tricky because this is holomorphic just for finite part. So you cannot apply functional equation quite quickly because the Archimedean part will contribute a bunch of poles, and that would make things problematic. Well, that's basically the background and what we know about this problem. Here's a geometric summary. So roughly we have two sides, algebraic side and an analytic side. We will look at the arithmetic quantity called n, where it refers to degrees of the field extensions on the algebraic side and the ranks of the general linear group on the analytic side. We expect the degree corresponding to the rank, and we look at these two ratios. Here are complete L functions. We look at complete L functions because we want to use functional equation. And for these ratios, we have static conjecture on the algebraic side and the Selberg conjecture on the analytic side. And we know n equal to 2 case, especially by the work of Shimura and Zagier, where for degree 3 and degree 4 case, we know the static conjecture hold due to the work of Chida and Van der Waal. But for higher degree, there's no idea. And for GL3 and GL4 case, it was not known. Not even for hell rank. Basically, when n is large, it's quite open. But we have the exciting dreams like Artin conjecture and Langlands conjecture, where this is basically what the background about this problem. And here's what we did. Roughly speaking, we proved this conjecture for GL3 and GL4. And here's a formal statement of the main theorem. Let F be a global field where let F be a number field. Cross-functional field is sort of trivial because we've already known the global Langlands. And let tau be an entire class character, and let pi be a Caspidal representation of some central character. And we can define the twisted adjoint L function to be this. This is the complete L function, Hack L function. When tau is trivial, then this is just the adjoint L function. So if n is less or equal to 4, then the complete L function is entire unless for some obvious reasons. For example, when tau is non-trivial, but pi is tau twist. In that case, the denominator is holomorphic, but the numerator would have a simple pole. That's the exceptional reason. So in particular, Selberg conjecture would hold for any Caspidal representation on GL3 and GL4. This is because the complete L function is holomorphic, and the Archimedean parts will have no zeros, so you can remove them freely, and the finite part will be holomorphic. We emphasize the complete L function not just because we can use functional equation, but it has some applications towards converse theorem. It should be some, this case should be the initial condition. I mean, maybe the initial step for using converse theorem. And in GL2, this will be enough to give you the Gilbert-Jacquet lifting. And for Hill rank, of course, this is not sufficient. But if you assume a very strong converse theorem of Piotetsky-Shapro, which says roughly characteristic would be enough, then this would in principle give you the adjoint lifting for GL3 and GL4. So in principle, this should have some applications in Langlands functoriality. But that's all big conjectures. And now we can look at, we can talk about the proof, or at least the idea of the proof. Recall that we have this Langlands implies everything diagram on this corner. We have some, we know some cases of Dedekind conjecture, especially for degree less or equal to 4. And recall that we expect the degree would be correspond to the rank on the analytic side. So it's a natural expectation that this adjoint L function is holomorphic for rank less or equal to 4. And this was investigated by Jacquet and Zagier in GL2 case. Because, in that case, say their idea was to make this diagram commutative without referring to Langlands philosophy and Artin conjecture. So roughly speaking, in GL2 case, Jacquet and Zagier proved that Dedekind conjecture would imply Selberg conjecture. And what we did is GL3 and GL4 case. And the main toolkit for this implication would be a variant of trace formula called Jacquet-Zagier trace formula. So let's talk about this trace formula. Let's first review this trace formula on GL2 and see how it works. So here's a formal identity of trace formula traces like on GL2. This K is the Euro-kernel function with respect to some test function, where in this lecture, test function would mean it's smooth functions having compactly supported modular the center, and it's by K invariant, and it has some central character. Matching the central character of pi, you are interested in. And this K naught means the contribution from Caspidal spectrum, and K infinity means contribution from non-Caspidal spectrum, namely residual spectrum and continuous spectrum. And this is an Eisenstein series. So we consider this integral. And this integral on the left-hand side is actually well-defined because K naught is decaying rapidly and Eisenstein series increases slowly. So the whole thing should be okay. But on the right-hand side, the integral may blow up. But so this is just a formal trace formula. And then Jacquet and Zagier investigated the P conjugacy classes in GL2. The reason to look at P conjugacy classes is to unfold Eisenstein series. Like you have this quotient. So here's a quotient GL2. And if you can unfold the Eisenstein series, then we will have a quotient by P over rationals. Therefore, this is the idea to compute the geometric side. Eventually, there will be some convergence issues, but eventually, when the real part of S is large enough, you have these expressions. On the left-hand side, you have a bunch of Rankin-Selberg functions. And on the right-hand side, the elliptic optic integrals will give you a bunch of Dedekind zeta functions of some field extension, and other optic integrals like hyperbolic or unipotent and identity will give you some distributions representing these L functions respectively. And this part will be kind of tricky, and let's just call it S. It comes from a non-Caspidal spectrum. And they verify that all these terms will be convergent absolutely and normally in some region. and in the red half plane actually, and say admit a Mellin-Morphic continuation. And then you can divide it on both sides by the dedicated zeta function of f, and you will see eventually you will have some, you have to have this represent expression. On the left hand side, it's actually an infinite sum, and this sum converges perfectly. And on the right hand side, you have 4 terms. This term actually comes from the elliptic optic integrals, and these two comes from the spectral side. This is from other kind of optic integrals like hyperbolic, unipotent, etc. And say look at all these terms carefully and find out the possible poles. There are just the 2 choices, a half and 1. And then they do spectral analysis for the left-hand side. This coefficient C pi and C depends on the test function phi actually, and you can varying the test functions to isolate individual adjoint L functions. Eventually, you will get a holomorphic continuation of each adjoint L function to this red half plane. Since this is a complete L function, you can use the functional equation to deduce Sarber conjecture for GL2 case. That's basically what Jacquet and Zagier did. So if you want to generalize their approach to Hell-Rank case, you will have a lot of barriers. For example, this part is actually an infinite sum of Mellin transforms of some Rankin-Selberg L functions, where in Jacquet and Zagier's work, they just treat it as a finite sum. So the convergence would be a problem. You can overcome this by using some sort of regularization. However, the tricky thing is that you cannot regularize the infinite sum. You can just, I mean, the tricky thing is that you can show the convergence of this infinite sum, but you still need to get to the Mellin-Morphic continuation. Mellin-Morphic continuation is still an infinite sum. You need to show the Mellin-Morphic continuation would be convergent. And for that thing, regularization does not work quite well. You need to introduce other new inputs. And for this part, say use the Poisson summation, but for non-abelian sense, Poisson summation is not available. And for Hell-Rank case, there might be many more subtle issues because the conjugacy class is more involved. Anyway, let's look at the Hell-Rank case. So similarly, we'll start with spectral decomposition. K0 is again the contribution from cuspidal spectrum, and this is the whole kernel, and this is from non-cuspidal spectrum. It has the spectral expansion like this, and these are Eisenstein series. What we will do is to apply Fourier expansions to this Eisenstein series. Eventually, we will have a combinatorial decomposition for this K0 as 4 terms. This term corresponding to the regular p-conjugacy classes from the geometric side, and this term corresponding to the constant term of the Eisenstein's the constant Fourier expansion of the Eisenstein series from spectral side. This corresponds to the non-constant term of the Fourier expansion. By non-constant term, I mean the Fourier coefficients with respect to the maximum unipotent or the unipotent of the Borel. And we will put all other things together as a singular part. Namely, this case singular would consist of both contribution from geometric side and the spectral side. Geometric side is just some non-regular p-conjugacy classes. And for spectral side, it corresponds to contributions from non-constant Fourier coefficients with respect to parabolic subgroups which are not Borel. So this thing will essentially not appear in GL2 case, because for GL2 there are just one proper parabolic subgroups, which is precisely the Borel. And then we will take the integral with against the Eisenstein series of the diagonals to get this decomposition after some manipulation. Where the left-hand side is there the infinite sum of adjoint L functions. There are 4 terms on the right-hand side. We will introduce these 4 terms one by one. I mean, at least I'll give you a rough idea of what they look like. And then we need to verify that the convergence would be okay when, at least when the real part of S is large enough. We can do this by variant Vasa's truncation techniques. Then we will need to find some mellomorphic continuation of these terms one by one. So let's look at the first term, the p-regular conjugacy, p-regular opti integrals. After some kind of computation, you will have this expression. Although it's kind of complicated, but eventually you can, generically you can think it's just of this form. This is the contribution from elliptic regular conjugacy classes. And these are ratios we looked at. This is the twisted Dedekind zeta function of E. So according to Dedekind conjectures, this would be holomorphic unconditionally. When n is less or equal to 4, this part should be holomorphic. That's one of the main reasons we can only obtain Selberg conjecture for GL3 and GL4. Because for GL5, I don't know how to prove this part is holomorphic. And the second term, the constant term from the Eisenstein series would be of this form, and the Q of S is entire. It's the sum factor from the integral representation. And you can read out possible simple poles from this expression. And in particular, it's a simple pole at the center if tau squared is trivial, namely when tau is trivial or tau is quadratic. And this blue colored function comes from the Eisenstein series. It comes from the flat section of the Eisenstein series used in the trace formula. And other terms are from constant term of some constructed auxiliary Eisenstein series. Initially, the initial formula for this definition for this thing is not factorizable. It's an integral over some rational quotient, so you cannot break it into local pieces. So what we can do is to rewrite it as a finite sum of factorizable integrals and look at and do some local computation. And each such factorable integral could be written as certain intertwining operators of certain constructed principal series. So you can use Langlands-Shahidi theory to get this expression. That's basically how we treat this this constant term. It's actually different from Jacquet and Zagier even in GL2 case because we are avoiding using Poisson summation. And for the non-constant term, the definition is this. Well, this is not actually the initial definition because the initial definition, this integral should be outermost. Here we switch the orders and moved it inside the sum, inside these sums. So you need to verify that you can switch the orders. So what we need to do is first show for the real part of S is large enough, we can show this integral converges absolutely. So we are free to switch orders. And this is an infinite sum running over proper Caspidal data. So all these Caspar forms are non-Caspidal. And we need to look at this Rankin-Selberg period as a function of the parameter. So we need to do some local computation as Piotrowski Jacquet did before. Bertelsky-Chaperon, I'm sorry. And so we will get convergence and continuation to some red plane, like the real part that's larger than 1. However, there's no stupid extension because this expression would have poles everywhere on the boundary. So what we will do is to make use of this Mellin transform. We'll shift the contour, and that's why we need to know the behavior of this function with respect to lambda, and that's why we need to do local computations as well. And here comes the tricky part. This is I don't have enough time to give full description of this thing, but the upshot is that it's holomorphic in the right half plane, and it has just two possible poles, and that's at the central point, it's at most simple. And this pole happens if and only if tau squared is 1. This is the definition of the singular integrals, and we treat it by unfolding Eisenstein series first. So the whole integral would factor through some unipotent quotient, and we then do some repair to show this singular kernel will cancel with each other when integral over some unipotent quotient, and the surviving terms would behave quite well over the remaining region. And by that, we can rewrite this thing as finite linear combinations of Artin integrals from smaller groups. And then we get convergence and holomorphic continuation from induction. So eventually we will get holomorphic continuation to some right half plane containing this region, so that we can use functional equation. And we know the information about the poles. But technically, this region is too large for me. What we can do is to get continuation of these terms to some open set containing the right half plane. This is some open set, so that we can use functional equation. And eventually, actually, you can take this region to be the zero-free region of Dedekind zeta functions. And then you need to, and then we will shift the contour to get a holomorphic continuation. We'll shift the term by term. There are many possible poles, but eventually there would be around n squared terms in the final precise expression. Like for GeoS3, there would be 20 or 30 terms, and we can show the absolute convergence for each such expression in this region D. As before, when the real part of S is large enough, we can use a variant of Arthur's truncation to show the absolute convergence. But when S is in the strip, namely the real part of S is smaller than 1 or equal to 1, things would be a bit tricky, because you cannot unfold the Eisenstein series, as the Eisenstein series does not converge absolutely anymore in that region. So what we will do is using techniques from analytic number theory to give estimate of these integrals. And we will bound these integrals by their counterparts, but with S large enough. So we can again use Arthur's truncation to show the absolute convergence. And that's how we prove absolute convergence of these integrals in the region D. And then we will determine all the poles explicitly of this continuation from the precise expression. And then there are n possible poles, which are like a half, 2/3, 3/4, etc. And the first n-1 poles are just a simple, at most a simple, where at s equal to 1, it might be multiple, but it's okay. It's okay for other reasons. And we then do some careful analysis for these precise expressions to exclude possibilities of all these n-2 poles. And but we cannot do this for the central point because it's just too complicated. Well, of course, for GL2, you can do brute force computation to exclude the possibility of the central point. That's what Jacquet and Zagier did precisely. The main reason is that you can, for GL2, the flat sections are basically Tate integrals. So it's okay. And here we will do some cheating ways to exclude the possibility of the central point. We will look at the root numbers of the adjoint L function. You know, when this is a simple pole, if and only if the character is either trivial or quadratic. And what we will do is to show that the global root number is trivial in these cases. So in conjunction with functional equation, we will see if this central point is a pole, it must be of even order. However, we know in priori that this is at most a simple pole. Therefore, it cannot be a pole. It cannot show up as a pole. That's how we exclude the possibility that central point is a pole. Therefore, we will get a holomorphic continuation outside s equal to 1 in the region D. And apply functional equation, we will get the main theorem, the Sato-Tate conjecture for GL3 and GL4. There are also other reasons that we consider GL3 and GL4 rather than GL5, because there are too many terms in the continuation. It's technically complicated. I can't handle that, and the whole continuation and the converge and verify the absolute convergence would be more subtle, because we need to verify, we need to study local properties of those Rankin-Selberg period as a function of lambda. Anyhow, we can do this for GL3 and GL4. And since I still have several minutes, let's talk about some applications of this result. First is a case of Sato-Tate conjecture on GL3. It's not a big result, but something interesting, I think. So basically, using an idea of Raman Krishna, we can prove for any cuspidal representation on GL3 of a number field, you can find infinite many places in certain given ray class, such that at these places the local representation are tempered. Here's a classical language version, and you know, the parameters here are of modulus 1, and the Hawk trace is lying in the unit disk. This is quite I mean this is some cases of Sato-Tate, where this is one of the applications of our main theorem, and I will leave 2 minutes on the further discussion related to endoscopy and beyond. First, the Jacquet-Zagier trace formula could be used in stabilization of trace formulas for SR2, and this would give basically some simplification of certain parts of Lebesgue and Langlands. It will give you a twisted trace formula. I mean, a trace formula twisted by the character. And the geometric part of the trace formula, a Jacquet-Zagier trace formula, could be used to refine some results on prime geodesic theorems. This was done by Han Wu last year, and require at least work on beyond endoscopy. Although they used the Artin-Selberg trace formula for GL2 to handle the Harris class number from the elliptical part, they related these Harris class numbers to certain L values. One can actually get this relation by considering Jacquet-Zagier trace formula directly and taking the residue at s equal to 1. So one probably can use Jacquet-Zagier trace formula to do beyond endoscopy and keep the parameter s until last step. Then you take the residue. So in principle, this might be might simplify things, or might even work for higher rank case. And Yannis Saklaridis told me last year T and Chen Wan are working in higher rank case using Jacquet-Zagier trace formula, and I hope they will make it. Well, I think that's all what I want to talk about in this lecture. Thanks for your attention.
Thank you, Liyang. You can't hear us, but we're applauding you. Thank you. Very nice talk. Results are beautiful, but also very technical. Do we have any questions? We have a few minutes for questions. If you have a question, you can either just speak up directly, or you can send me a chat and I can announce you. There's a question for Hector Montiel. You can go ahead and ask your question.
Oh, okay. I'll check it.
He says he doesn't have a mic. Okay, let me see. I can ask it for him.
Okay.
Oh no, he didn't type it. So I don't know. He just said, okay. So we'll wait for his question. So you're telling me that if I go to 5 and higher, it just becomes too many terms to handle? Is that?
Well, that's just a technical reason. The main reason is that we don't know Dedekind conjecture for degree 5.
I see. It's known when closure is solvable or something like that, right?
Yeah. That's the main reason. Yeah.
Okay, so here is Hector's question. Are you aware of some basic consequences in number field of Dedekind conjecture?
So can you make it more specific? So like which kind of basic consequences are you expecting or are you looking at?
So if the ratio is entire, what it means for general properties of number fields?
Well, the conjecture says that for general number field extensions, the corresponding ratio should be entire. That means in terms of Galois representation, the induced representation would contain a trivial factor, and others are kind of irreducible in the sense that the corresponding Artin L functions are holomorphic. It's yeah.
No, in general, Dedekind conjecture is more like a test case as how much you know about towards Artin's conjecture.
Yes. Thank you.
I see Fredun. Fredun, do you have any questions? There's more chat here. Erez, did you want to ask a question? Yeah, go ahead. You're muted. All these mathematicians struggling with their devices trying to get unmuted. Okay, so while we wait for Fredun and Erez to get unmuted. So you're saying this also gives maybe another approach to beyond endoscopy?
Yeah.
And it's working, you think, for I mean, I know those people who are trying to extend even beyond GL to like GL3, they find it extremely complicated. So you think?
Yes, even for GL2 is quite complicated.
Yeah. But do you think this approach using the other trace formula is simpler?
Well, honestly, I haven't tried in detail, but in principle, it should somehow simplify the proof.
So I think there's everybody's having trouble unmuting themselves.
I think, am I unmuted? Because I think
yes, we can hear. Yeah.
I mean, it was a beautiful talk. Thank you. I mean, it's just it's unfortunate that you can't go beyond 4. I mean, it's clear it becomes very difficult and technically impossible. But I mean, it's an important conjecture. So that's as you said, the trouble is on the Dedekind side. That is
Yes.
that too. So that's a project by itself. Good luck with it.
Okay, any other comments?
I'm glad I could unmute myself because I
Yes,
transitioned.
Erez, I see you're unmuted now. You want to ask a question? No. Saul, did you have a question? You're unmuted as well.
No, I'm fine, thanks.
Okay, good. Okay, good. Look, it looks to me like people are trying to digest what.
Now we can clap.
Yes.
Thank
But
you.
here, no, the problem with Zoom is if we all applaud at the same time, you can't hear it.
Yeah. Okay.
You only hear one sound.
One
stream.
at a time.
One at a time. Yeah, we'll go through everybody and you can applaud. So if there are no further questions, then let's thank our speaker again and close the session for today. We're probably going to take a vacation for 2 weeks. So there won't be a number 3 seminar for the next 2 weeks, and then we'll reconvene in August. Okay, so thanks everybody. Again, once again, stay safe and healthy wherever you are, and we'll see you soon.
You too. Thank you. Bye-bye.
Thank you.
Bye.